Hi, I'm Professor Goins. In this video, I'm going to look at the idea of a potential function. Okay, start with the definition. If f is a vector field on an open set D, and if there is a scalar function f, so lowercase f, for which f is the gradient of f, then we say that f is a potential function for f. So if this vector field is the gradient of some scalar function, then that scalar function is the potential function. Okay? Questions. 1. How do we know if a vector field has a potential function? Notice I've got 3 components here, so this is going to apply for the vector function as 3 components. How do we know if a vector field has a potential function? And then second, if it does have one, then how can we actually find it? Okay? Theorem. A vector field has a potential function if and only if the following 3 conditions are satisfied. What I do is I take various partial derivatives of the components and see if they're equal to each other. Okay, so I won't read through all of these. We'll use those here in the examples, but I want to see if, for example, if the partial derivative of p with respect to y, so that would be the third component, is equal to the partial derivative of the middle component with respect to z, and so on and so forth. So we have to verify that those 3 equations are all satisfied. Then this vector function, vector field, would have a potential function, and then we can go about finding it. All right, let's look at the following example. Determine if the vector fields have a potential function. It doesn't say to find one, we just want to see if it actually has one. And then if it does, we can search for or show you how to find it. All right, keep in mind that the components of this, remember this is the first component is m, the middle component is n, and the third component is p. So this is m, this is n, this is p. So let's compute the various partial derivatives. All right, so this is to compute the partial derivative of p with respect to y. So for this function here, the partial derivative of p with respect to y, so p with respect to y, the partial derivative is 1. And then the partial derivative of n with respect to z, so dn dz. N is the middle component, partial derivative with respect to z is 1. Okay, so the first equation is satisfied. Let's look at the middle equation. The partial derivative of m with respect to z. M is the first component, partial with respect to z is 0. Next thing that I want to see if that's equal to the partial derivative of p with respect to x. So dp dx. P is the third component with partial with respect to x is 0 because there's no x's there. First and second equation are satisfied. Now let's try the third one. So this would be the partial derivative of n with respect to x. N is the middle component. Partial derivative of this with respect to x, so that's an x squared. That gives me a 2x. And then I have the partial derivative of m with respect to y. M is the first component, and the partial derivative of this with respect to y would be 2x. All 3 equations are satisfied, therefore this vector field does have a potential function. In the following example, I'll show you how to find it. Let's go through part B and see if that is a potential function. Part B. Okay, so again, this is m, n, and p, so the first, second, and third components. Condition says take the partial derivative of p with respect to y. P is the third component, partial with respect to y would be 0. and then the partial of n with respect to z, so dn dz. N is the middle component. Partial derivative of this with respect to z would be 2y plus 2z. And those two are not equal to each other. So therefore, this does not have a potential function. You could check the next two conditions just for practice with taking partial derivatives, but it doesn't matter if they're equal or not because the first condition is satisfied, so we can go ahead and stop there. Okay, so now we know this vector field here does have a potential function. Let's see if we can find it. So next example, find a potential function for the vector field f given by 2xy, x squared plus z, and then y. Okay, so let's see how this works. So we know that it has a potential function. We verified that in the previous example. And back to the definition, we know that the role of a potential function, the relationship between the potential function and the vector field, is that the vector field is the gradient field of the potential function. What that means is, symbolically, is that the vector field f is equal to the gradient of this function f. And we're going to use that equation and the fact that we know what this is equal to, the vector field, to find the components of this vector. Well, we'll use that, we'll set components equal to each other, and then we'll use that to solve for f. Because remember that the gradient of a function is the vector field generated by the partial derivatives of the corresponding components. That means I take the partial derivative of the function f with respect to the first variable, partial derivative of f with respect to the second variable, and then the partial derivative of f with respect to the third variable. If the vector field is equal to this, that must mean that the 2xy is the partial of f with respect to x, for example. So that's our starting point, is to set this component equal to this component. Okay, so we have 2xy is equal to the partial derivative of f with respect to x. With this equation right here, what can we say about the function x? F, keeping in mind that f is a function of x, y's, and z's. What this says is whatever this expression is, I take the partial derivative with respect to x, I get 2xy. Well, that must mean that 2xy came from x squared y. So I know that I had an x squared y there. Notice the partial derivative of this would be 2xy. But I also could have some other terms. Well, what other terms could I have? Thinking that I'm taking the partial derivative of f with respect to x, anything here that has y's or z's, the partial derivative with respect to x would be 0. That means that the unknown terms I'll list as a function of y and z. So it's an unknown expression with y's and z's. So there's the starting point for finding my potential function. Now what I'm going to do is I'm going to use the middle components. I know that the partial derivative of f with respect to y is given by x squared plus z. Okay? So if those two middle components are equal, let's set them equal to each other. So that would give me x squared plus z is equal to the partial derivative of f with respect to y. Now at this point, we're going to solve this one slightly different because I now have the building blocks of the potential function. So I'm going to, rather than doing sort of an antiderivative idea that I did here to get started, I'm now going to, for the partial derivative of f with respect to y, we can compute the partial derivative of this with respect to y. So that says that x squared plus z is, oh, sorry, that's supposed to be x squared. So x squared plus z is the partial derivative of this with respect to y, which would be x squared plus the partial derivative of g. Remember, that's a function of y and z with respect to y. Canceling x squareds from both sides, this gives me the following equation. Z is equal to the partial derivative of g with respect to y. So what do I know then about the function g? It could have y's and z's in it. I know that when I differentiate with respect to y, I get just a z. So here's one thing I can say about the function g of yz. How did I get a z if I differentiated with respect to y? Well, I must have had a yz. I could have also had like a plus 5 or plus 6, but what else could I have had? Well, I know that this is only dependent on y and z. No x's, so there's no x terms here. Could it have had other y's? Well, no, because when I differentiate something with respect to y, I'm going to get something that's non-zero, but everything else over there, I only have a z over there. It could have had terms with z's in it. I could have had, say, a 5z or a z cubed or e to the z, because the partial derivative of those with respect to y would be 0. That means that the remaining terms here could be could involve z. Okay, so therefore I'm going to take this expression and I'm going to substitute that into here to get my to get more information about the potential function f. Therefore, I know that the potential function f consists of the following. I know it has an x squared y, and then g, the function g. Well, the function g has a yz, and then an unknown h of z, so I'll put plus h of z. Finally, what I'm going to do is I have to solve for h of z, figure out what that would be, and we can pin that down using the third component here, that the partial derivative of the scalar function f with respect to z must be y. All right? So this gives me that y is equal to the partial derivative of f with respect to z. And what I can do is I can differentiate the function f with respect to z. This part would be 0. This part here, yz, the partial with respect to z would be y, and then plus the derivative of h of z with respect to z would be h prime of z. Since that's an ordinary derivative, I don't need a partial derivative notation, so I can just use a prime. All right, therefore, h prime of z is 0, which means h of z is a constant. So I want to give a specific function, so h of z could be, well, first of all, it's equal to a constant. And then I'll pick a specific function, h of z is equal to 7. Could be any constant, could be 0, pi, anything. Therefore, the potential function that we're looking for is this, f of x, y, z is given by x squared y plus y z plus 7. So a couple of things. One, this is the function that you took the gradient of to get the vector function we started with, to get this vector function right here, this vector field. 2, notice that the 7 here was just an arbitrary constant that I chose. I could have chose any constant as long as it doesn't involve x, y's, or z's, meaning that if a function, a vector field has a potential function, it actually has infinitely many. And they only differ by a constant, so I can't have any other x, y's, or z's in here, but another potential function could be x squared y plus yz minus, say, pi squared. So the only other variations that I can have is a different constant on the end. All right, in this short video, I showed you what a potential function was, how to determine if a vector field has a potential function. If a vector field has a potential function, how then to find it. What I haven't shown you is what is a potential function then? Okay, so we know that it's the gradient, or what I took the gradient of to get that corresponding vector field, but what is they used for? Well, what we're going to see in another video when we talk about the fundamental theorem of line integrals is the potential function will play the role of an antiderivative. So see that in another video.